Hey everyone, and welcome to another explainer brought to you on behalf of Forge College. Today, we're diving into a really fascinating engineering blueprint, recursive function patterns in Solidity. Now, if you've been following along with the Solidity from Zero track, you know this fits right into our advanced function implementation module. I know. Recursion sounds super theoretical, right? Like something out of a dense computer science textbook. But stick with me because, as you'll see, it has incredibly practical and sometimes wildly expensive consequences when you're building in Web 3.
Okay, let's quickly run through our blueprint for today. We're going to cover the next level up, explore this concept I call the nested tray metaphor, and break down the categories of recursion. Then we'll get into the nitty-gritty with gas, frames, and mechanics, look at refactoring to safety, and finally wrap up with our safe recursion takeaways. Let's jump right in.
Section 1. The next level up. Coming off our last lesson on patterns and best practices for modifiers, you're probably feeling pretty good about handling control flows. Well, think of recursion as the next big power-up in your toolkit. Think about the comparison for a second. You already know that modifiers are absolutely brilliant for extracting repeated checks. They keep your access control centralized so your main function stays nice and clean. Recursion does something really similar, actually. But instead of extracting guard code, it extracts repeated architectural structures. It does this via self-calls, meaning you don't have to duplicate complex nested structures or loops. It's kind of like a cheat code for cleaner architecture.
Moving on to Section 2, the nested tray metaphor.
To really master recursion in Solidity, we need a good mental model of how it actually behaves inside the EVM. Formally, recursion is just a function calling itself to solve a problem. It breaks the problem down into smaller, identical instances, always building toward what we call a base case. But let's keep it grounded, okay? Basically, it's just a highly controlled nesting of tasks. You're taking a massive problem and slicing it into tiny, manageable pieces.
And this brings us to my favorite way to visualize this: physical cafeteria trays. Imagine a stack of them. Every single time a function calls itself, boom, you stack a new tray. That tray holds your local values, your pending work, and instructions for what to do next. You just keep stacking those trays until you hit the very bottom one. That bottom tray, that's your base case. Once that bottom tray finishes its job, it pops off, handing its result to the tray right above it. Then the next one pops, and the next one, all the way back up until your top-level result is completely resolved. It's a really neat way to visualize function frames opening and closing.
All right, Section 3, Categories of Recursion.
Now, not all recursive functions are created equal. You're going to encounter a few specific flavors. First, we have direct recursion. That's when a function simply calls itself. It's super common and great for natural divide and conquer problems. Then there's indirect recursion, where function A calls function B and B calls A. Honestly, this gets complicated really fast, so you won't see it too often. We also have recursion over storage, where you pass indices to access storage directly, rather than copying massive amounts of data around. But consider tail recursion for a moment. This is when the recursive call is the very last action in the function. Conceptually, it feels simpler, right? Like handing off a tray without leaving any unfinished food on it. But here is the massive catch for us Solidity developers. The EVM doesn't reliably provide tail call optimization. No way around it. So even if your code looks beautifully clean, it's still eating up physical stack space and gas unless it's optimally compiled.
Which leads us nicely into Section 4, gas, frames, and mechanics.
This brings up a pretty obvious question. If recursion is so elegant, why not just recurse forever? Well, in Web 2, an infinite loop might just crash your user's browser. Throw a stack overflow. It's annoying, for sure, but mostly harmless. In Web 3, though, an infinite loop literally drains your wallet. Every single operation costs gas, and the EVM is unforgiving.
Because of that, if you're going to use recursion, you absolutely must distinguish between your call types. Internal calls are implemented as simple jumps to a different region inside the same contract. They're significantly cheaper. External calls, on the other hand, use opcodes like call or delegate call. This creates an entirely new message call context. Doing that recursively is wildly expensive, and worse, it opens you up to devastating reentrancy risks. So the golden rule here? Stick exclusively to internal calls when you're doing algorithmic recursion.
Let's dig a bit deeper into that per-frame cost. Remember our trays? Well, every recursive depth allocates a brand new call frame. That means you get a linear gas increase for every nested level. But you know what the real silent killer is here? Data movement. If you pass large data structures, like arrays, by value, the compiler allocates memory for copies at every single invocation.
Going back to our metaphor, instead of pointing to one shared tray of food, you are literally cloning the entire buffet onto every single tray you stack. It multiplies your gas cost by the depth of your trays. Always pass compact parameters like indices instead.
Okay, Section 5, Refactoring to Safety.
So what do you do when you've written a brilliant recursive algorithm, but the gas limits make it just too dangerous to deploy? We have to redesign it. Consider this really common problem. You need to do a depth-first traversal of a tree. Maybe it's a referral network where unit node IDs are mapped to arrays of child IDs. Now, a naive recursive traversal works beautifully if the tree is shallow. But what if that data is user-submitted? What if some bad actor intentionally creates a massive deep chain just to break your contract? You're going to hit unbounded depth limits, you'll run out of gas, and the transaction will revert.
To fix this and build something predictable, we can actually refactor from recursion to iteration. Here's how it works. Step 1, initialize an explicit memory stack with your root ID. Step 2, create a flat while loop that just keeps running as long as that stack isn't empty. And step 3, pop an ID off the stack, process it, and push its children right back onto the stack. By doing this, we're replacing those super expensive, deeply nested EVM call frames with a flat iterative loop and an explicit memory array. Suddenly, your gas behavior becomes completely predictable. It's a total game changer.
Finally, Section 6, Safe Recursion Takeaways.
Let's do a final inspection and lock in the key engineering rules you really need to remember. The absolute crucial point here is balancing the elegance of divide and conquer logic with the really harsh constraints of EVM gas and call frame overhead. First, always verify you have a correct base case. Never ever leave a recursive loop open-ended. Second, always pass compact parameters. We're talking single indices or accumulators, definitely not giant memory arrays. And lastly, have the wisdom to refactor to an iterative loop the second your maximum depth becomes unpredictable or starts relying on untrusted user input.
I actually want to highlight this quote directly from the source material because it really hits the nail on the head. Combining explicit limits with iterative refactors gives you both expressiveness and production-safe behavior. See, you don't have to abandon recursion entirely. It's a beautiful way to express complex logic. You just have to rigorously control its parameters and its bounds.
Well, this sets us up perfectly for our next explainer in the Advanced Function Implementation module, where we'll be tackling overloading and overriding practices. We'll learn all about how different function variants interact with visibility and inheritance. To make sure you don't miss it and to explore the rest of the Solidity from Zero track, be sure to head over to forge.college and continue your Web3 education.
As you head back to your code editors today, I want to leave you with this final thought. Will your next recursive algorithm be a brilliant engineering shortcut or an expensive gas trap? Keep those nested trades in mind, watch your call frames, and write safe contracts. Thanks so much for joining me on behalf of Forge College, and I'll see you in the next explainer.